Hi everyone. In this video, we will present about the engineering component design project, which consists of the final product design and the analysis of the product. First of all, let me introduce my group member from group 7. There are Glenn Hanaya Sitompul and me Laila Nurfitria and Laili Murianti. In this video, we will discuss about several main points. For the first one is about the process of designing the product. The second one is the proposed product. And the third one is the final product, which consists of the selected product, the finalized specifications, the finalized product drawing, and the stress analysis, and also the safety factor. The process of designing the product. In here, we start from the identification of needs, and then after that, we have to know the problem definition, and then we start to create this synthesis, and then we need to conduct the analysis and the optimization, and then we do the evaluation after the analysis on optimization. And for the last one, we need to do the presentation of our product design and the analysis. The next one will be explained by Glenn.
Okay, here we have the proposed product, and then the proposed product is arrived from our previous design. There are three design issues, and then from those the three design, we are having discussion that the final product will be derived from model 1 and model 3. And then from there, we are having the four design derived from those combination. And then here we show you the four derived combination. After long discussion, we are finally decided to use the model D to be our final design. However, this design needs to be foldable expanded to overcome the lack of bed facility in hospital. And then the next objective, this design needs to expand up to 180 degree as a bed, and also it needs to have the adjustable height so that the doctor can use it professionally to check the patient. Okay, next. Here we have the model 1 and model 3. This is the design designed previously on first report. We have the model 1 and model 3. Mainly, we are taking the bed from upper part of design 1 to be on our model D, and then we are taking the road from model 3 to be our final design. Hopefully by this design, the chair can be flexible and then making smaller space compared to the ordinary bed. Next, and then for the final product, we are having discussion that the material be stainless steel with the family of authentic type 304, and then the maximum adjustable height is up to 1 meter. And then here we show you the dimension of the chair. Next, this is our final product. On the left side, we have the detailed measurement of the product with the detailed dimension we have discussed. And then on the right side of the slide, we have the 3D view of the product. Here we see that most of the design is made from rod and pins. Okay, next presentation will be delivered by my friend Layli. Layli, time is yours.
Okay, as explained by Glenn, we already have the a final product that already has the dimension, and then we try to analyze by saying the most critical part in the system of the mechanism design. And here is the FPD, or the free body diagram, as a system in the critical part of the mechanism design. And in this mechanism design, we have some assumption which are neglecting the friction, since we have four wheels that we use, and then we set the applied load is 1500 Newton, and the mechanism design is made of stainless steel austenitic family type 304 that has some mechanical properties which are yield strength with 250 MPa, tensile strength 600 MPa, and the Young modulus is 190 GPa. And here is the free body diagram of the critical part as a whole system. Next will be explained by Leila.
Now, in this part, we will discuss about the first part of the free body diagram, which is the bottom part, or at rod AB. In here, we need to find the reaction forces of point A and B that already applied with 1500 Newton. And from here, we calculate and find the value of the reaction force RAY is equal to 890.63 Newton, and for the reaction force RBY is equal to 609.37 Newton, and for the reaction RAX it is equal to RBX, which is 0. And for the next, it is the second part of the free body diagram, which is the adjustable height on rod FC. In here, we need to calculate the allowable load by using the energy strain density formula. In here, we need to identify whether the second part, FBD, is failed or not. Therefore, we use the energy strain density formula such as shown in the slide, which has both font and using the stainless steel austenitic family properties, which already explained by Layli in the previous slide. And here we divide the calculation into three parts, which is for the part FE, we calculate the energy strain density formula is equal to 64.75, and for the part ED, the energy strain density formula is equal to 189.97, and for the part DC, the energy strain density formula is equal to 523.19. And after we already know the value of energy strain density, we can calculate the maximum allowable load at the three parts, which is part DC, ED, and FE. For the part DC, the allowable load is equal to 1590.5 kilonewton. And for the part ED, the allowable load is equal to 961 kilonewton. And for the part FE, the allowable load is equal to 491.5 kilonewton. From here, we set the allowable load from the calculation, which is equal to 491.5 kilonewton, which is at the FE part. In here, we can find the allowable stress by using the yield stress formula. Therefore, the allowable stress is equal to 125 megapascal.
As explained by Lila, she has explained the two parts of the critical point in this mechanism design, and the last part is the most critical part, which is the handling set road GH analysis. And here it is shown the free body diagram of the handling set, and here it is shown the cross section that we use. It is has the thick 5 centimeter and the width is 2.5 centimeter. By analyzing this handling seat part, the safety factor of the mechanism design can be obtained, and we need to find the reaction force that act on the handling backbone and head, which is RGY sin 150, and the handling foot, which is RHY sin 150 degree. Next, after that, we can find the reaction force by using the moment at G or moment at H. However, in this analysis, we try to analyze by using the moment at G, which is the sigma mg equals to 0. We can compute all of the known values, which is the applied load, and then we can obtain the RHY equals to 987 Newton. And then after that, we can determine the another reaction force that act on the handling backbone and head, which is by using the sigma force. And then the sigma force equals to 0. Compute all of the known values, and then we can obtain the RGY equals to 2013 Newton. And then after that, we can draw the shear force diagram and the bending moment diagram. To find the shear force diagram, we have some value here. It is the shear force, and then we can directly draw to the like as shown in the figure beside. And based on the figure, it is give us the maximum shear force, which is 1006.5 Newton. And then we can after obtain the shear force diagram, we can obtain the shear stress maximum by using the 3 over 2 V max over A. And then we can compute all of the known value, and then we can obtain that the it is our mistake. It should be the tau max, which is the maximum shear force, which is 1.21 MPa. Next. After obtain the shear force diagram, we can continue to find the bending moment diagram. As we know in the previous course, we already explained that the bending moment diagram is the area can be obtained the area over the curve in the shear force diagram. And then based on this calculation, we can obtain the maximum bending moment is 3 to 7.11 Newton meter. And then after obtain the maximum bending moment, we can determine the maximum normal stress that we can obtain in this mechanism system by using this formula. Sigma max equals to M max over S, where S is 1 over 6 BD square, where B and D is the dimension of the cross section that I already explained. And then we can compute all of the value, and we can obtain the maximum normal stress is 31.45 MPa. Next. Okay, after obtaining the maximum shear stress and the maximum normal stress, we can determine the principal stresses. The principal stresses can be used to determine whether this mechanism that we design is fail or not. And then the sigma, by using this following formula, we can obtain the sigma maximum is 31.50 MPa, and the sigma minimum is minus 0.05 MPa. As explained in the class, we can determine the safety factor after we obtain the sigma maximum and sigma minimum by using the MSS theorem. And then after that, we also able to determine the maximum allowable shear stress, which is by using the sigma max over sigma min over 2. Then we can obtain the sigma allowable stress is 15.78 MPa. And after that, we have conclusion that since the sigma maximum is less than the allowable sigma stress, and the maximum shear stress is less than the allowable shear stress, therefore this mechanism is can be success, can be said it is success, and it is not fail. And then after that, we can determine the safety factor by using the MSS theorem. Then we can obtain the safety factor is 7.92. Next. And here is the reference that we use. This reference is used to find the material selection and the properties of the stainless steel. That's all from us, and thank you.